Hey guys, today we're going to talk about the quantum mechanical model or the wave mechanical model, and then also electron configuration. So many people contributed to this quantum mechanical model that we have, and it keeps updating. One of the first people that contributed to this model is de Broglie, and he was the first to suggest the wave-particle duality of matter. So up till de Broglie's time, we thought of electrons and atoms as particles. Now we believe that they also behave like waves, so they have a dual nature. Schrodinger was another person that contributed a lot, and he mainly came up with these equations to make predictions about where the electrons may be found in an atom. So he came up with these equations that we solve for functions to graph to show us the probability of finding the electrons somewhere. Heisenberg came up with his uncertainty principle, which says that the more we know about the speed or the momentum, the less we know about the position of that electron. So we can't know both at the same time. The more we know about this one, the less we know about the position. The more we know about the position, the less we know about the speed or the momentum. So it's only possible to predict where an electron will probably be at any given time rather than knowing its exact whereabouts. So from all of this, we kind of are able to draw these 3D probability maps, which are just functions that are graphed as 3D graphs. We put them all on top of each other, and we get these maps where there's shading, and the darker the shading, the higher the probability of finding the electrons somewhere in a given shell. Shell means level. So I've always used energy levels. The CED by College Board, they use energy shells. Shell or level are interchangeable, so energy level or energy shell. So these maps that show us the probability where there's high shading or high probability of finding electrons there, we call those high probability areas orbitals. The maximum number of electrons to occupy an energy shell or energy level is 2n squared, n being the energy level. So let's say I want to know how many electrons could be in the third energy level, so I do 2n squared with n being 3 because it's the third energy level. So that would give me 18 electrons possible maximum for the third energy level. So each of these shells or levels are then divided into subshells or sublevels, S, P, D, F. And so let's look at these pictures here. So this is the S sublevel. It only has one orbital. So like there's one map that we draw or one graph that we draw. These are the P sublevel, and it has 3 orbitals. So remember, these are 3D graphs. So they look like dumbbells, whereas S looks like a sphere. So those dumbbells in the P sublevel have 3 orbitals, one in the X plane, one in the Z plane, and one in the Y plane. Then we have the D sublevel, and there are 5 of these orbitals. And we have the F sublevels, and there's 7 of these orbitals. So S's are the lowest of the sublevels in energy, and they look like sphere, 1 orbital. P's look like dumbbells, and there's 3 of them, or 3 orbitals. D looks like a 4-leaf clover, and there are 5 orbitals. And then F looks like a complex shape, is what your textbook calls it. I think it looks like a flower, but there are 7 orbitals. And again, lowest in energy is S, then P, then D, then F. Theoretically, there's an infinite number of energy levels and sublevels in an atom. However, the elements that we've discovered so far, at least in their ground state, only occupy the first 7 energy levels and just the SPDF sublevels. But theoretically, there's an 8th energy level, a 9th, a 10th, an infinite number. And then same thing with the sublevels. There's SPDF, and then there's theoretically G, H, I, J, and so on. So like we said, the number of sublevels is equal to the level number. So for example, the first energy level has 1 sublevel, the second has 2 sublevels, the third has 3 sublevels, and so on. These sublevels or subshells, S, P, D, and F, are split into, like we said, 1, 3, 5, and 7 orbitals respectively, and each of these orbitals can hold up to 2 electrons. And to occupy the same orbital, those two electrons need to spin in opposite directions. So usually to show an orbital, like in an Akbao diagram, we either draw a line or a box, and the electrons are represented by arrows. So if we show that there are 2 electrons in this orbital, we do 1 up arrow and 1 down arrow. Same thing if you do lines. So that doesn't mean that one of them is spinning up and one is spinning down. It just means they're spinning in opposite directions. This table here shows you how we came up with that 2n squared. And I think it's a good visual to understand, like, how many sublevels and levels and all that and orbitals. So the first energy level or energy shell, whichever you want, that's your n, right? Has only one sublevel, and it only has the s sublevel in it. And s only has one orbital. So the first energy level has a total of just 1 orbital. Each orbital takes 2 electrons, so I can only put 2 electrons in that first energy level. The second energy level has 2 sublevels. It has the s and the p. S has 1 orbital, P has 3 orbitals for a total of 4 orbitals. Each orbital takes 2 electrons for a total of 8. Third energy level has 3 sublevels, S, P, and D. 1, 3, and 5 orbitals. Altogether, they are 9 orbitals. Each orbital takes 2 electrons, so that's 18 total electrons. Fourth energy level has 4 sublevels, S, P, D, and F. 1, 3, 5, and 7 orbitals for a total of 16 orbitals. Each orbital takes 2 electrons, so total is 32 electrons. The fifth energy level has 5 sublevels, S, P, D, F, and theoretically the G is also available. 1 orbital, 3 orbitals, 5 orbitals, 7 orbitals. G would have 9 orbitals for a total of 25 orbitals. And so 50 total electrons because each orbital takes 2 electrons. Sixth energy level has 6 sublevels, S, B, D, F, theoretically G and H. 1, 3, 5, 7 orbitals. G would have 9, H would have 11. They go up by 2s. And so all together there are 36 orbitals. So each orbital takes 2 electrons, so we get 72 electrons. And so this is where we're getting the 2n squared from. And so on, obviously, if you have the 7th and the 8th and the 9th energy levels and so on. So let's talk about Akbao diagrams or orbital diagrams, they're the same thing, or electron configurations. Whether you're drawing an Akbao diagram or an orbital diagram or electron configuration, you are basically showing the distribution of the electrons among the orbitals of an atom. So both of these show the distribution of electrons among the orbitals in an atom. Okay, and there are 3 principles that we go by when we are drawing those orbital diagrams or showing those electron configurations. The first one is the Akbao Principle. And basically the Akbao Principle, Akbao is a German word that means build up, and we're building up in energy. So basically we are saying that electrons fill orbitals from lowest to highest energy. So we fill them up in terms of energy. We go low to high. Overall, the first energy level is lowest in energy, then the second, then the third, then the fourth, then the fifth, and so on. But if you look at the sublevels, because the S's are lowest in energy, then the P's, then the D's, then the F's have a lot of energy, right? Because of the number of electrons that could be occupied in there, right? Like S can only take up to 2 electrons because it has 1 orbital. P can take up to 6 electrons. So there's more repulsion because you're forcing electrons to be in the same sublevel. D has 10 and F can take up to 14, right? So the more electrons you have, the more repulsion and the more energy that sublevel has. And so if you have something like a 3D, that might be slightly higher in energy than a 4s, for example. And so we fill it up in terms of lowest to high energy in terms of orbitals, not necessarily the whole energy level filled up first before we go to the next. Hund's rule says that we get the lowest energy when we have the maximum number of unpaired electrons. So energy is where there is a maximum number of unpaired electrons. Now, nature prefers low energy, right? The lower your potential energy, the more stable you are. And so nature prefers things to have low energy. That means they're more stable, they're not likely to change as much. And so that's why the orbitals are filled from lowest to highest energy. The electrons fill the orbitals lowest to highest energy. And also we want to make sure that we are filling those orbitals in a way that would minimize the energy as well. So let's say that you have oxygen that has 8 electrons. 8 electrons total, right? And so you take your 1s, and that takes up to 2 electrons. Then you have your 2s, and that takes up to 2 electrons. And then you have your 2p. I'm going to draw it in 2 different ways here. The p has 3 orbitals, so it takes up to 6 electrons. But if you look at oxygen having 8 electrons total, we already put in 4, so we only need to fill this up with 4. So one way is to do 1, 2, 3, 4. Another way is to do 1, 2, 3, 4. This is lower in energy, and this is what actually happens. This is higher in energy, and it does not happen. The reason is because, remember, electrons repel each other, and so the more spread out they are, the better. And so if you put 1 in each of the orbitals first before you pair them up, that's going to give you the maximum number of unpaired electrons. These electrons are unpaired, which is good compared to having them paired like this, with this one being empty. When you have more room, you should spread them out. So this is not correct. This one is correct. And finally, the Polyexclusion Principle. We kind of already said that up there. Basically, we're saying that each orbital takes up 2 electrons, but so in order for the orbital to take 2 electrons, they must spin in opposite directions. So in order for an orbital to hold 2 electrons, they must spin in opposite directions. Which we show by the up and the down arrow. Okay, so let's actually try to look at how we can come up with those electron configurations. So if you remember last year, we were able to do this from the periodic table. Make this a little thicker. So we have the energy levels first, and so the energy levels kind of correspond to the periods. So here's your energy level. This is energy level 1, 2, 3, 4, 5, 6, and 7. Then we have the sublevels. So we're going to start with the S sublevel. And so the S sublevel has 1 orbital. And so it can hold up to 2 electrons. And so you look for a block of 2 on the periodic table, which is right here. And so this is my S block. And so this would be your 1s, 2s, 3s, 4s, 5s, 6s, and 7s. Then we have the P. And the P sublevel has 3 orbitals, and so it can take up to 6 electrons. So you look for a block of 6, and you see that there's the P block. Now that helium actually belongs with the S's here. Some people argue that helium should be here on the periodic table, but they place it here because it's a noble gas. So this is actually part of the 1s. That's the second block that goes here. So the P actually starts with the second energy level. There is no 1p, so this is the second energy level, so this would be 2p, 3p, 4p, 5p, 6p, and 7p. Next is the D sublevel, and the D sublevel has 5 orbitals, so it takes up to 10 electrons. And so you look for a block of 10, and so there's your D block. If you remember last year, though, D was a little wacky. Remember, we used to call it wacky one-off? Because it's one off from the count. So this is the 4th period, but this is not 4D. It's actually one off of that, so this is actually 3D. 5th period would be 4D. It's one off from the count. This would be 5D and 6D. And this right here belongs there, so just the lanthanum is 5D and just the actinium is 6D. And then finally we have the F sublevel. So the F sublevel has 7 orbitals, so it takes up to 14 electrons. And so there's your F block. And if you remember last year, we called it wacky 2 off, because it's 2 off from the count. So right here, this belongs there, which is the 6th period. So 2 off from that would be 4. So this is your 4F. And this one belongs right there in the 7th period. So 2 off from that, this would be your 5F. So if you're doing electron configurations or Akbao diagrams and you're looking for a certain element, what you do is you just go through the periodic table, all the boxes there, until you reach the element that you are looking for. So let's do a few to practice here. So we're going to start with beryllium. So beryllium, I should have here. There we go. So beryllium is right here. So you go through your periodic table, you see the 1s first, and there's 2 boxes. So 1s, and there's 2 boxes, meaning there are 2 electrons, 1 up, 1 down. Done with the first period, then you go to the second period, 2s. 2s has 1 orbital, and we have 2 boxes, so that means both electrons are there. The electron configuration is a shortcut for the orbital diagram. So you do it the same way, except instead of drawing arrows, you put superscripts. So you write first 1s, and there are 2 electrons, there are 2 boxes, so you put it as a superscript, and then 2s, and then you put it as a superscript having 2 electrons there. So when you add up your superscripts in an electron configuration, or when you add up your arrows in the orbital diagram, you should end up with the total number of electrons for that. Valence electrons are the electrons that are in the highest energy level. Electrons in highest N for energy level. So you look at this or this and you say, which one is your highest energy level? Well, the second energy level is your highest energy level, and there are 2 electrons in that energy level, so 2 valence electrons. Let's look at nitrogen. So nitrogen is right here. And so I go 1s, and I have my 2 electrons. Then 2s, and I have my 2 electrons. And then I go to the 2p. The 2p has 3 orbitals. I need to draw all 3 of the orbitals, but I only need 3 electrons. 1, 2, 3 in the 2p. So I put 1 in each first because I want a maximum number of unpaired electrons. If I wanted the electron configuration, I'd say 1s, 2, then 2s, 2, then 2p, 3. And you can get this from this or just from the periodic table, 1s, 2, 2s, 2, and then 2p, 3. Valence electrons are the electrons in the highest energy level. So my second energy level is my highest energy level. So all of these are in that highest energy level. There are 2 electrons in the S, 3 electrons in the P, so total is 5 valence electrons. do blue. Okay, next one is neon. Trying to keep my periodic table up here. Okay, neon is right there. So as I go through, I say 1s with 2 electrons, 2s with 2 electrons, and then 2p with my 8 electrons. 1s with the 2 electrons, 2s with the 2 electrons, and then the 2p, I fill it completely with 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Or if I wanted to do the electron configuration, 1s2, 2s2, 2p6. My valence electrons, my highest energy level here is the second energy level. And so these are all in the second energy level. There are 2 in the s, 6 in the p, for a total of 8 valence electrons. Okay, next one is sodium. So sodium is right here. And so after we get to neon, it kind of gets long to write all this. And so there is a shortcut called the noble gas core, or the noble gas shortcut, where the element that you want, what you do is you look at the noble gas that comes before it. So the noble gas that comes before sodium is neon. So what you do is you write out neon in brackets. And when you do that, that means you've gone through the whole periodic table up to where neon is. So you've gone 1s2, 2s2, 2p6 already. So now all you have to do for sodium is you write the neon in brackets, and then you do whatever comes after neon until you get to your element. So in this case, all we have after that is just the 3s, and it only has 1 electron. So 3s. So you write neon and then the 3s with 1 electron. You can do the noble gas shortcut with orbital diagrams or with electron configurations. So if I want to do the electron configuration for sodium, I can do neon in brackets and then just 3s1. Highest energy level here is the third energy level, and there's only 1 electron there, so it has 1 valence electron. Okay. In your notes, you have your periodic table, so I'm not going to be going back and forth. Just look at your periodic table there. So calcium, so we're going to do the noble gas shortcut for it. So the noble gas that comes before calcium is argon. And then I guess I will go look at it. So calcium is right here. So argon comes before it, and then all I have is 4s, and there's 2 boxes there. So 4s and 2 electrons in there. Argon, 4s2. My highest energy level is the 4th energy level, so I have 2 electrons in that 4th energy level, so 2 valence electrons. Okay, iron is next. So iron is right here. So my noble gas that comes before it is argon, and then I have 4s with 2 electrons, and then I have the 3d with 1, 2, 3, 4, 5, 6. So let's do that here. So argon, then we have our 4s with 2 electrons, and then the 3d with 6. So you go 1 in each, 3, 4, 5. Before you go back, pair them up in 6. So for my electron configuration, same thing, argon, 4s2, and 3d6. Be careful with your valence electrons. What is your highest energy level here? Highest energy level is 4th energy level, right? 4th energy level is higher than 3rd energy level. So these are your valence electrons. And so you have 2 valence electrons, not 6. So it's not necessarily the one that goes at the very end. If you remember last year, we looked at some exceptions. You do not need to worry about these exceptions. Last year, we looked at the chromium family and the copper family. Know that there are some exceptions, but you do not need to know what they are or worry about them for AP Chem. Okay, let's do a few more. So we'll do zirconium. So zirconium is right here. So the noble gas that comes before zirconium would be krypton. And then we're going to go 5s2 and then 4d2. So krypton, 5s2, 4d2. Valence electrons, 5th energy level is your highest energy level, and so you have 2 electrons there, so 2 valence electrons for that one. Next is lanthanum. So lanthanum, let's go up. Lanthanum, I'm kind of hiding it, it's right here. So lanthanum belongs right there, and so the noble gas that comes before it is xenon. So we're going to write xenon, and then 6s2, and then 5d1. So xenon, 6s2, 5d1. Highest energy level is a 6th energy level, and so you have 2 valence electrons. And the last one we'll do here is uranium. Let's see, what color did we use? Let's do this one. Right there. And so uranium, this belongs here. And so the noble gas that comes before it is radon. Then we're going to have 7s2, then 6d1, and then 5f3. So let's write that down. So we have radon in brackets, then 7s2, 6d1, and then 5f3. Highest energy level is the 7th energy level, and so 2 valence electrons. So you'll notice that the transition metals and the inner transition metals seem to all have 2 valence electrons, right? Like iron and zirconium and lanthanum and uranium. The reason for that is the S sublevel is always going to be higher in energy than the Ds or the Fs, right? Because remember, Ds are 1 less and F is 2 less. So the S electrons are typically going to be your highest energy level, and so those are going to be usually 2 electrons. There are exceptions, of course, like we saw last year, but they're usually 2 electrons. And so most of the transition metals and the inner transition metals, so all of these and these as well, are usually going to have just 2 valence electrons. Okay, now let's look at ions. If I have an ion, how can I come up with the electron configuration for it? So for me, I always look at the electron configuration for the neutral element, and then from there I come up with my electron configuration for my ion. So let's look at an example here. So magnesium with a 2+. So I first do just magnesium. I'm going to do it on the side here. So just magnesium would be 1s2, 2s2, 2p6, 3s2. So then, this is neutral magnesium without a charge, but this tells me that I have a +2 charge, which means I've lost 2 electrons. Well, which 2 electrons are you going to lose? The valence electrons, which are these. And so the electron configuration for magnesium ion is 1s2, 2s2, 2p6. Most of the time, the ions, or the atoms, lose or gain electrons in order to become more stable, which means to have a noble gas configuration. So a lot of times, not always, but a lot of times your electron configuration for an ion is isoelectronic to a noble gas. Iso means same, electronic means electron configuration. So this is the same electron configuration as neon. So the magnesium is going to lose 2 electrons, so it becomes stable like neon. Okay, let's look at bromide. So neutral bromine, I'm going to use the noble gas shortcut here. It's argon, and then we have 4s2, 3d10, 4p5. Okay, but that negative means we've gained an electron. So we're going to add 1 more electron here, because the 4p can hold up to 6, and we only have 5 there. So I can add the 1 extra electron to there. So it's going to be argon 4s2 3d10 4p6. And this is isoelectronic to krypton. Okay, let's look at Fe2+. So I'm going to do neutral Fe. And neutral Fe, I'm going to use the noble gas shortcut argon. And then I have 4s2 and then 3d 1 2 3 4 5 6. Okay. Now this is telling us that we lost 2 electrons. Which electrons do we lose or gain? The valence electrons, right? Which electrons here are the valence electrons? These are. So those are the 2 electrons that I'm going to lose. So this is actually argon 3d6. Now let's look at the 3+. So if I have neutral iron, then I have argon and 4s2 3d6. I'm going to lose 3 electrons. So I first lose my valence electrons, right? My valence electrons are these, and so I lost 2 of those. I need to lose 1 more. Well, once I lose all of the ones that are in the 4th energy level, then now these are my valence electrons. So I'm going to lose 1 of these to make it 5. So argon and 3d5. Okay, let's look at the next question here. It says, how many unpaired electrons are in manganese? How would we know that? Well, you'd have to draw your your Akbao diagram or orbital diagram. So let's do that. Our argon precedes manganese. It's argon. Then we have 4s with 2 electrons, and then the 3d. And manganese would have 5 in the 3d. Remember, you put 1 in each before you go back and pair them up. No need to pair them up because we only need to draw 5. And so how many unpaired electrons do I have here? Well, these are paired, but these are not paired, so 5 unpaired electrons. Okay, we want to identify these. So 1s2, 2s2, 2p6, 3s2, 3p5. So I'm going to go ahead and go to my periodic table. 1s2, 2s2, 2p6, 3s2, 3p1, 2, 3, 4, 5. That looks like it's chlorine. So my answer here is chlorine. Okay, how about this one? 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Let's go back to our periodic table. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d1. Is that where we stopped? That looks like it's scandium. Good. How about this one? 1s2, 2s2, 2p6, 3s2, 3p6, 3d1. Ooh. What's the difference between this one and that one? Looks like this is missing, right? So what does that mean? How can you have the 3d before that 4s2? Well, that means it's an ion. It has lost those 2 electrons. So that would be scandium with a 2+ charge, right? So be careful. If we caught this because they give us this one, and so we realized, oh, something's wrong with this. But be careful if you're only given this, that you're checking that it's in the correct order, that you're not missing anything. Can it be anything else? Yes, it can. What if it was titanium 3+? Can it be that? Let's look at titanium. So neutral titanium is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d2, right? So if it's a 3+, that means I lost these 2, and then I lost one of those to make it a 1, right? Could it be vanadium 4+? Yes, it can, because neutral vanadium would be all of this, then 4s2, 3d3. So if it lost 4 electrons, it would lose those 2, and then 2 of these to make it 1, right? So it could be a variety of different things. Most likely it's probably scandium 2+, but theoretically it could be a whole bunch of different things. Isn't that cool? All right, last thing we're going to talk about in this topic here is the idea that we have paramagnetic and diamagnetic substances. So what does that mean? Diamagnetic, or elements, diamagnetic means that all the electrons are spin paired. Electrons are spin paired. And it turns out that when all your electrons are spin paired, these elements are weakly repelled by a magnetic field. And the way that I remember this is di means 2. So I think all my orbitals or all my electrons are spin paired. That means like paired means 2, right? Like they're, all of them are 1 up arrow, 1 down arrow. They're all paired. Paramagnetic means you have unpaired electrons. And when you have unpaired electrons, they are a little bit attracted to a magnetic field. And this applies to ions as well. So let's take a look at these here and try to figure out, are they diamagnetic or paramagnetic? So how would you do that? What you do is you look at the cation. Don't worry about the anion. So in this case, we're looking at the Fe2+. This one is the Zn2+. This one's copper 2+, manganese 2+, calcium 2+. This one, Fe3+, and V3+. So what you're going to do is you're going to look at the electron configuration of the ions, not the neutral element, but the ion. So think about Fe, and then take 2 electrons, and think about what the electron configuration would be. And if it's all spin paired, then it's going to be diamagnetic. If it has some unpaired electrons, then it's paramagnetic. So I want you to stop the video right now, try to come up with the answers here, and then check my answers after. So stop the video and work on it. So welcome back. Hopefully you got these answers. I got that all of them are para except for the zinc 2+ and the calcium 2+. And if you want to look at my work here, these are all the electron configurations for the ions. Remember that you remove the s electrons first if it's a transition metal before you start removing any of the d electrons. All right, have a great day, guys.